2.2, we start off with set operations. We're going to cover in this video about half of the section. So definition 1, let A and B be sets. The union of the sets A and B denoted by A union B is the set that contains those elements that are either in A, B, or in both. Intersection of two sets A and B is the set containing the elements in both A and B. So they must be present in A and they must be present in B. Two sets are called disjoint if their intersection is empty. That means there's nothing common between them. Now be careful when you do the union. If you take A union B, if you count all the elements in A and all the elements in B, you have to take out the overcount, the elements that are in both. Unless the set is disjoint, then this here would be 0 because there's nothing there. But if it's not disjoint, you gotta be careful with that part. Difference. Let A and B be sets. The difference of A and B, and the ordering is very important. If they say A minus B is the set containing those elements that are in A but not in B, you're taking B out. The difference of A and B is called the complement of B with respect to A. Definition 5. Let U be the universal set. The complement of set A denoted by, we put A with a bar on top of it, is the complement of set A with respect to the universe. Therefore, the complement of set A will be everything in the universal set except for A. So, A minus B is denoted by a Venn diagram right there. There is A, but you took out B. And the complement of A is everything other than A. On page 144, I'd like to look at some problems. And again, this is the first half of the section. Suppose set A is the set of sophomores at your school, and set B would be the students in discrete math of the school. Express these sets in terms of A and B. So, A, the set of sophomores taking discrete math in your school, that's both. That's A intersected with B. That's people that are sophomore, or students that are sophomore, and taking discrete math. The set of sophomores at your school who are not taking discrete, so A intersected with not B. The set of students at your school that are either are sophomore, well here you could say really A minus B if you wish, that works as well. The set of students at your school who are either sophomores or taking one or the other or both. The set of students at your school who either are not sophomores or are not taking. Given the set A is the following letters, B, let's see, A, B, C, D, and E. Okay, A union B, well pretty much since A is already in B, that's going to be all the elements in B because they're included in both. So that would be A, B, C, D, E, F, G, and H. Set B, A intersect B would be the common, which is all the elements in A in this case. That's not always the case. That is set A really. A minus B, so you take all the elements in A minus the elements in B. Well, that would be all the elements in A minus the ones in B. That's really the empty set. There's nothing there. If you take all the elements in B, you took out everything in A as well. B minus A would be all of these minus those. That would be the set E, F, G, and H. And I just want to move this down here. Oops, that's not what I meant. There we go. Prove the identities. Now the table I didn't show you yet because there's a lot of properties. I'm gonna go over that in the next video. Prove the identity law in table 1 showing that A union the empty set is A. Well, we start with A union the empty set would be X such that X belongs to A or X belongs to the empty set. But the empty set is empty, there's nothing there. So this is really saying X such that X belongs to A, which is set A. And if I go for B, show that A intersected with the universal set is A. Well, let's see how that works. A union the universal set is the elements that are in A, and because it's intersection, and the same elements that belong to the universal set. That is X such that, but all the elements, okay, the universal set looks like a union. I've been trying to separate it. So let's do it this way. So you can separate it between union and the universal set. So, but all the elements in the universal set and in A, that's pretty much the elements in A, which is set A. So the null has nothing, and the universe has all of them. Number 10, show that set A minus the null set is A. Well, let's see. A minus the null set, that is X such that X is in A and X are not in the empty set. But the empty set doesn't have any elements in it. So this is really saying all the elements in A, which is A. And to show B, the empty set minus A, that would be all the elements in the empty set intersected with X does not belong to A. Because you're taking those out. So that is X, so you want them in both such that X belongs in the empty set only. That is the empty set. There's nothing there. Problem number 12. Prove the first absorbing law. I guess in the table, you can look at the table, it's in the lesson, shown that if A and B are sets, then A union A intersect B is A. Well, here we say if we let X belong to this set, then that means that X such that X belongs to A or X belongs to the set A intersected B. That's how the definition works. So if X belongs to A, and the first case, case 1, if X belongs to A and X belongs to A and B, then that is pretty much proven because you're looking for a union. That's pretty much set. That's not a problem. So case 1, if X belongs to A and X belongs to B as well, then that'll work. That's pretty much proves it. That's set A, not a problem. And if you go the other way around, if you go by X belongs to A, then X belongs to A union A intersected B, because, so if in the first case, if X belongs to this set and this set, you're safe. But if X only belongs to this set, right? If X belongs to A, then it automatically belongs to A or B, even if this is not working, even if X does not belong to A intersected B, because it's an OR. So since it's in A, automatically that proves it backwards. Find the sets. A minus B is this set. B minus A is this set. A intersect B is this set. Well, let's see. Oh boy. Let's set A and B. Okay. Find the sets. So A is, and let's see. B minus A is 2. So what do we have? We have 1, 2, 3, 5, 6, 7, 8, 9, and 10. That's everything. 1, 2, 3, 6, 7, 8, 9, and 10. That is true. So set A minus B union with A intersected with B. If I make set A 1, 5, 7, 8 union with 3, 6, and 9, then that would be 1, 3, 5, 6, 7, 8, and 9. If I take B minus A, if I take B, and that is B minus A union with A intersected B, that would be 2, 10 union with 3, 6, and 9. That would be 2, 3, 6, 9, and 10. So this is where we're going to stop for this video. We'll continue this on the next video.